Hey Thibault, just quick question.
Yes.
Hi. Yeah, I saw it looks pretty good. So basically, Mac joint and Graph joint recover the sharp boundary, which is pretty nice. So did you only use a petrophysical information, or you also have some sort of like a non-L2 norm?
Like a what? Sorry, what type of norm?
Yeah. So you use like the petrophysical information. Did you
No,
also use like non-L2 regularization?
no. Everything is L2 at this point for this
Oh,
first.
every okay, even the sharp boundary thing.
Yeah. So like while I do the cluster, like I reweight things, so it helps a bit for the definitely the smallness term is dominant over the smoothness,
Okay.
and after that I have a few, like, let's say I have a few tricks on my sleeves. For example, when I've reached when I reach like a stable reference model, like it's not changing anymore, because that's what it's happening. Yeah, like under the hood is that I'm changing the reference model along the way at each iteration.
Mm-hmm.
And when the reference model, like, and for the last step, like when the reference model is not changing at all, I include that reference model in the smoothness, so to kind of like highlight this sharp boundary that we recovered in the smallness. But
Okay.
it's kind of like, but this sharp boundary, like, I got it during the inversion, and add the reference model in the smoothness is actually just a final trick at the end to speed up the conversions. But that's actually not completely necessary.
Okay. Okay. So yeah, basically the the model in space is not there's no sharp model norm, but it's more like in the parameter space.
Yes.
Okay. Good.
Yeah. So for this type of result, to do a joint inversion, like, we need some sort of link between the two, and we do that through the petrophysics. And even for this, like, we try to cluster, but we need some, like, we need to actually put some like additional information in the inversion for that. So like that's where the petrophysics using a Gaussian mixture is used. So just as just as a quick snippet, that's, for example, that's my representation of the physical property. So it's a Gaussian mixture is basically, it's just a weighted sum of Gaussian. So for example, here, like, if I have two physical property and I have two units, that will be the two Gaussians that represent it. Or like you can, or like in 1D, that's what it will look like. It's like as a slice. So like, and every slice would be Gaussian too, but, and here, so like what I call cluster 1, cluster 2 is basically like each of the work unit.
Mm-hmm.
So that's the information I want to put inside the inversion. And like I invert both for the geophysical data, but I also try to recover the petrophysics information. I'm telling that, oh, I want my model to reproduce the geophysical data and to have this type of distribution.
Mm-hmm.
And so that's the full framework on how I do it. And like as a start, this portion is that what we always do. Like, we have some initialization. So m naught is my initial geophysical model. Theta naught here is how I present my petrophysical model. So if we have none, just like it's the input is just like null or whatever, and it's just not gonna be used in the inversion. And Z naught is it's my membership. So it's the variable that's hold, telling like which cell belong to which work unit. So also in the normal inversion, we're not gonna, like, we usually start from a half space, so that Z naught will be just okay, background everywhere, and we're not gonna actually change it. So So then we do the normal inversion. We have some geophysical data, and we use like a gradient method on our objective function phi, and we check our stopping criteria, and we loop over that until we reach the stopping criteria, and we have a final output. So in the normal case, that will just be m. But here, my interest is like to recover the geophysical model M. I want to also recover a petrophysical model. Like why I'm doing that is that I don't assume that I have a perfect knowledge of my petrophysical model over an area. So I use this prior information as a prior, like as a reference model, if you want. So I'm also fitting along the way the petrophysical data, and that actually really helps because you're clustering slowly after each iteration instead of trying to have like some hard constraint. You're bringing it to a cluster solution slowly through the iteration. And I'm also interested into having to recover this membership classification, which, if you want, is my it's gonna be a quasi geological model. Like this cell, we find that this cell belongs to work unit 1, this cell belong to work unit 2. So it's kind of like an interpretation of your inversion. So how we do that is actually, so all this part is like, yeah, it's what we do usually in SimPEG. And that's the part I really had, and most of it's happened in the directives. So the very first step, and we're gonna see here, is that after each gradient step, after each iteration, so I got a certain geological model at a certain step, and I want to cross it with my petrophysical data that I know prior. And with these two information, I'm gonna fit a new petrophysical model that take into account both my prior knowledge and the current geophysical model. So that's what it looks like, for example, in 1D for that step. So here in gray, that's my prior knowledge of the petrophysical data. That's what I want it to look like. In blue here, that's my histogram of my current geophysical model at a certain iteration. And so the distribution I'm gonna use is gonna be the one in black. So that's gonna be it's like a mix between the two distribution. Like so like the concept is very simple, but then after that in the inversion, you have actually a lot of flexibility that each parameters of the Gaussian has its own weight. So you can say, oh, I'm very confident into that mean, but I'm not confident into that mean. I'm very confident into that covariance, but not that covariance. So even like you have, there is an information of proportion. I think this unit makes up 20% of my area, and the other 80% is background. So you can give, that's all sort of prior information you can input into the.
Hey Thibault, just clarify.
Yes,
is the blue histogram your likelihood function?
Excuse me, Dikwan. Okay, sorry, I could not.
The blue one, the blue histogram, your likelihood function.
Like the blue histogram. Yes, so that's the
likelihood.
That's the histogram of the model, and yeah, that corresponds to the likelihood portion of my of the objective function I fit for that. And then yeah, the prior is
dash. Yeah.
The prior is the dash, and so the posterior estimation is
solid, right?
Is like, so like the map EM here, that means maximum a posteriori expectation.
Okay.
That's what it is.
Okay.
So like the map is really like, yeah, the posterior estimation.
Okay, got it.
And EM is the algorithm that is used for this optimization.
Mm-hmm.
And Thibault, with that, are you assigning uncertainties on your prior? Like, do you assign an uncertainty with the mean and the covariance? Is that how, like, the average, I guess, is taken between your current distribution and the prior?
Yeah. So yeah, I'm not talking about uncertainties, but I'm talking about confidence into this value. That's so. So if you want for each parameter, it's come down to a weighted average of the parameter, and so how you weight that is how much confident you are. And the way I've set it up, it's fairly simple. Is that if you put a confidence of 1, is that you trust as much your geophysical model as your prior data. And if you go, if you have an infinite confidence, you're just not updating your petrophysical prior. And a confidence of 0 just means that you have no prior.
Okay.
That's how do you set that? Like you have some set that, or like?
Yes, I have weights for that. So yeah, you have that's a user input saying that how much you kind of you trust each of your.
So what's your default?
My default is 1, like saying that, oh, like if I have like in the synthetic world, it's like, oh, I trust as much geophysical data as my as the geophysical data as my petrophysical, because in synthetic, like all of them are kind of true, so you know them very well. But you can definitely tame down things like, and really each one can be weighted separately. So if you just know the mean but none of the other parameters, you can have like some confidence in the mean and set everything else to 0, or you can even just put, or if like something I've tried to sometimes is like you only constrain on the covariance. So you're saying I don't know anything about the mean of my units, but I want them to be fairly tight. So you're gonna cluster, but you don't know around it what value, and that actually works fairly well sometimes.
So when
and I think it's come down a bit. Like when I do the thing, it looks a lot like when I think there is a strong link when you only constrain on covariance. There's a strong link with the iterative reweighted square. It's kind of come down almost to the same thing, like with a weighted matrix that you update along the way.
It kind of makes sense. It's like get the document. There's always see the real with the measuring and what the response would be, right? With the machine downhole, like it would be a shift of like a timestamp on everything. So it makes sense that the medium is free.
Yeah, so that's the one thing that it's like every parameter has its own confidence, and so you can definitely play a lot with that.
So just to check, when the confidence is 1, so that black curve is going to be a dashed line? Is that right?
No, here you have the example right here. It's a confidence of 1. Like things are like just an average 50% of each of the things. Like if you want the black to be the dash one, that will mean an infinite confidence, or very large confidence.
Yeah. So that when confidence is 0, that black goes to blue.
Yes. That's how I weight it, and it was kind of like making sense. So
you must have another parameter to change the contribution from petrophysical. How much contribution is from petrophysical? How much is from the observation?
But I'm not sure I understand your question, Dikwan. But what I think is that like all this weight confidence it's basically how much weight you give to each parameter of your prior.
Okay.
I think, correct me if I'm wrong, Dikwan, but I think the question he's getting at there is how are you, like, is there a beta parameter or a tuning parameter that's just controlling how well you fit your petrophysical data versus the geophysical data? Is that what you were asking, Dikwan?
Yeah, pretty much. Yeah.
Okay, so like everything happens in the smallness. So actually, your objective function, like for each geophysical iteration, works exactly the same as usual. So all these steps that I do, I will be able also to build it, for example, around the UBC code. If I was building that into like, I don't know, like a MATLAB, etc. And then so there is still a beta parameter that weight between the data misfit between the geophysical data and my smallness now is my misfit between my current model and the petrophysical data. So I end up having two target misfit, one for geophysical data, one for petrophysical data, and I have directives to reweight the beta, for, like to try to achieve the target misfit for both of them. So I have like the way I do that is actually like in the very first step I do as usual, I do a beta cooling. Like I'm not automating it, but I'm doing a sort of beta cooling because I'm trying to fit the geophysical data first. And then I'm actually doing a beta warming, a bit like what Dom is doing also for the L1, to push the clustering, but keeping the data missing low for the geophysical data.
Okay.
So there is like a two-phase thing. Like you first go down in beta and then go up, fitting first the geophysical data and then the petrophysical data. But the clustering is also happening. Like I will have an animation on the next slide to show you what's happening.
Okay.
So that's this step. I'm updating this petrophysical model at each step, and how I use this. So then how I use this black curve is actually, so for each cell I'm gonna attribute one of the two clusters, for example, and then I'm gonna change the smallness weight and the reference model according to the distribution. So like if a cell, if I have a cell that has this value, MUF is gonna be like the mean of this cluster, and the smallness weight is gonna be the covariance of that cluster. So that's the next step, like where I'm saying like, oh, I need to update my my membership, my geophysical model. So that's this step. So I'm using this as a classification, and I can also use like some prior information. If you're pretty sure that a certain area belongs to this rock unit, you can say, oh, the membership for this set of cells is fixed. It's always whatever the values are inside, it's gonna be this rock unit for sure. So you have both. A lot of this work is actually having like a mix of having global information. Oh, I know my petrophysical data are this, and I'm trying to recover a model with this range of non-convex value, and you try to locate that, but you can also include also on top of that local information to force that. So it's a bit what it means here, but like here what I'm showing is that so everything is, as I say, happening in the smallness. So it's very similar to what we usually do. I have a weight, I have my M, and I have an MREF. But notice now that this weight depends on the current petrophysical distribution and the membership. So Z here is basically just the most likely unit considering my prior knowledge and the current value of the cell. And then WS becomes the covariance and MREF becomes the mean. And here, this W here, it's like all your like cell weight that you usually use. So for example, for the grav and mag, even if I'm using this type of framework, I can still put depth weighting or sensitivity weighting. It's gonna come into that. So I'm multiplying the covariance and the sensitivity weighting all together. So all the information is there. All the usual thing is here. So that's one of the main message I want to say here. I'm not removing anything. If you were doing something in a Tikhonov style, it's likely to work with that framework too, and I've made sure that everything is kind of compatible on that side. Like if for GravMag, if you want sensitivity weighting, go for it. It helps, and we can include that. And from the geophysical point of view, the iterations are the same, but we are changing the objective function at each iteration. So that's why, for example, I'm saying like that's something you can actually build around the UBC code at some point, if that's something really does.
Covariance, like the big sigma is a constant in this case for each of the groups. Is that right?
Yeah, so so if I have 3 work units, I'm gonna have 3 different sigma. And,
so it's a constant value. So you're not optimizing more further away from the center of your cluster. There's no distance from the center of your cluster. Let's say you have a model parameter that is like sitting on the edges of everything, right?
Yeah.
It's part of group 1. You're just gonna get the same penalty as everything else in the group 1.
Yeah, but I've not put that slide here, but okay. So, but your probability gonna be very low. So so actually your value gonna your probability so you want to, if you want here, you want to really maximize your probability, and you have a very low probability, so that's gonna show up just in the value of your objective function, but also the way you do it. The way you do it here is so it's a quadratic. So if you're very far away, your gradient is gonna be just higher.
The distance from minus 10.
Yes.
But I thought that you're updating the variance matrix.
Yeah, at each iteration.
Which is the width of the graph.
Yeah, pretty much. So here that's the animation. So I actually put it in a bigger thing. So that's a different step. So here I have the Tikhonov inversion, and here I have the Petrov inversion. So, and the dash here is the MREF. So that's a different iteration. So that's what we get with the Tikhonov. But here that's the Petrov. So here you see that I'm changing the reference model at each iteration to try to guide it. And so here that's kind of like the histogram. So here, I have really very narrow unit. It's just 0, 1, and minus 0.5. So my covariants are extremely small. But that's something I can in a simple example like this, easy to recover.
And Thibaut, do you have to specify how many clusters there are?
Yes.
Yes. So I'm not looking for how many clusters at this point. There are ways to do it. I've not dived into that type of thing yet. But the way I look at how they do it is, I fear that might get out a bit of hand, because it's usually they start from a large number of clusters, and then you decrease it. But at some point, at the limit, you can have a cluster per cell. So it's
yeah.
So I'm not but what you can do is saying that, oh, I have petrophysical data for 2 work units, but I know there is a third one that I know nothing about. So you can specify having 3 clusters, and you put some confidence into your petrophysical data for the 2 first work units, and you let the third one free.
Okay.
That's where having all the parameters, having its own confidence really can have a big role. Because you can definitely condition some work unit different than other, or not condition some work unit compared to other.
And how's it cost? Start or in terms of numerically, what's the cost?
The map EM thing is actually very fast, so that's it's really not too bad. So if things are a bit slower, but not that much. Maybe each iteration, maybe 20-25%, not too much. And there are maybe things that are not optimized at some point. As I have a lot of global and local information, there are some things that forming the matrix and to visit, it's kind of visiting each cell to see, okay, what's your information at this point, right? So I have a lot of nested loops that might be able to optimize some way, but I wanted something that worked at the beginning more than something that's fast. But at least I don't have outside for loop. If I have for loop, it's always in a nested loop. So in Python, the nested loop are not too bad. So that's what so that's a linear example. So that's very easy to see. Okay, what's happening, and we're trying to. So that's what's happening under the hood. And it's easy. Now, I am able to fit it to different different thing in SimPEG. So I have a time domain EM example. I have the 2D resistive 2D resistivity with sensitivity rating from them. So that's the sensitivity rating with Tikhonov. That's the sensitivity rating with the petrophysical constraint, and that's the joint 3D inversion. So,
Thibaut, did you try the DC example without the sensitivity reweighting, but with the petrophysical constraints? Like, was that a necessary piece if you have the petrophysical information?
It works. It works much better to have the sensitivity reweighting. I have the example without the sensitivity reweighting, and I'm actually just getting like some sort of it's still like I will still get some banana shape, but I will have banana shape cluster in the model recovered at the top of it.
Oh, okay. So
it's still clusters, but it's not like you definitely see the banana shape of the sensitivity still. So it works, but to get the very final result like this, that's actually helped to have the sensitivity reweighting. And as it's there, I don't see any reason to not use it.
You tried when your reference is wrong, for instance, let's say your mean is wrong.
Yeah.
Let's say true was 10 siemens per meter, like a 10 meter, for instance, but you put 50, for instance.
Mm-hmm.
How, do you have an example, how well you did? Or
I tried a bit. I have some example, but I have not really optimized or really played with that. So the thing is, if it's wrong, it might you're gonna have issue to fit your petrophysical data. You're not gonna be it's gonna be hard to fit. So there are so one way to one way for that is just maybe decrease your confidence in that value then.
Right. But my question there, because you're still updating your view, right?
Yes.
You have because your physics has some sensitivity to get the true value.
Mm-hmm.
But then because that confidence step was actually kind of averaging.
Yeah.
And the information from you're averaging. There's probably some chance actually you can get there. But what I'm
so maybe you're gonna you might get a smaller volume, for example, for conductivity or that type of.
There's something on uniqueness. So but if there's actually a sensitivity where actually I can get the true a very tight sensitivity for a certain value and value.
Yeah.
Then do you think it has a chance to get the a right model, or because you're still updating the reference?
Yeah. So if you're too far from the value, it might
not asking too far. I'm just thinking of a positive case. You're just off by a factor of 5. Not that bad, but still.
I would say that you might have a hard time then achieving the petrophysics misfit, because it's gonna try to bring it closer and closer, even if you don't and so from the petrophysical data you might have your model here, and then what you want to bring in here. So it might say that your misfit's is not that well. So then I guess what I would do is try to rerun the inversion with a smaller confidence, because if you put a smaller confidence, for example, for the mean, that's just going to mean that the mean of a cluster are going to be closer to the mean of the model than the mean of your prior. So that's one way. And it's also almost like an inverse problem. It's kind of the same setup. It's like a posterior estimation. So you have the M here is your likelihood or your data misfit, and you have a prior, which is your smallness and weight, etc. So if you stuck, you can think of doing same thing as like a beta cooling, but you decrease your as you go along the inversion, you try to decrease your confidence into the you start to decrease your confidence into the petrophysical prior, but increase your confidence into the actual geophysical model. That's something you can do. It's just like, it's possible. There is just a lot of, and I've implemented it. It's just like a lot of moving pieces. So I guess that it's possible, but then after that, it's like up to the user, or like there is still a user input saying, like looking at things like, oh, maybe I will need to include some sort of a cooling on the physical data to get something better.
So I'm just imagining a situation where, like, I got to pick a physical data.
Yeah.
There should be some bias, right? Like, a lot of reasons why it could be a little bit different, or like dramatically different. Usually different. And so, like, because there's some errors, and then the workflow that you think, okay, I ran first with that physical data.
Yeah.
I put a confidence 1. Okay, I got some results.
So it's 50-50.
But I haven't got like a target mister for my physical point.
Yeah.
So the next step, then, are you going to like adjust your confidence, or are you going to adjust your like a value for physical data, mean or whatever, the variance or whatever? Like what's kind of? Like,
I will adjust the confidence, because like your petrophysical data, it's your kind of your data, of like it's come maybe from all like other information, borehole survey or lab measurement. So it's not like you can definitely switch changing a bit.
Mm-hmm.
But my first try would be to play on the confidence, because that's a user parameter more than the data.
Like the median, or sorry, what days on petrophysical?
Yeah, I mean, like change your confidence into your petrophysical model.
Right. So the worst case here is like then petrophysical data was kind of useless. The worst case, because I'm getting like a decrease my confidence level. Then if I'm going close to 0, I'm getting actually the output without the petrophysical confidence.
Yeah, pretty much.
Mm-hmm. But the confidence could still happen on the Gaussian, right? So you could increase your confidence in the mean, just to shift the mean, but still keep
the covariance right. Yeah, that's
you need to be part of a group. Could you have because the usual problem is that the background is unknown, right? So we'd like to have a fix of reference model, constant reference model, find that value, but then the inversion. That's the full heterogeneity for the rest, right? So do you have to be part of could you have a single median and then the rest is just free to change? You know what I mean?
I mean, if when you do the Tikhonov style, it's like you have to be part of the group. Like your membership cannot be like unknown, because that's what determines your even just your reference model. You don't have you always put something as a reference model. Even if it's 0, it's not null, not a value. Like the Tikhonov, the Tikhonov style version. You have one cluster with mean, nref, covariance, whatever weight things you input in. You're not changing it, but it's just its covariance is fairly wide, and you try to find something like a model that for each shell is around that nref value.
The way you use that, let's say we have a single group.
Yeah.
Your covariance is still affecting everybody. Like, could you have a single reference model, a single group, but you have some of those small parameters that are not affected by the distance from the distribution of the background?
But if you have a single group, you have a Tikhonov.
Well, you have the extra term that you're measuring how much you're pulling on it, right? It's all in the smallest term right now.
Yeah.
Could you have also another layer that has smoothness also, which allows you to move freely outside of the.
Oh, so basically you're basically saying that W, or your weight smoothness is 0, or pretty much saying that the covariance is infinite, so it's like a constant, the probability of taking any value is the same. It's kind of like that means that you put your WS value for this cell, so to be 0. But yeah, you cannot be not part of a group. Like even when you, yeah, like if you want, like when you do Tikhonov, it's just saying that you have one group, but with a very large covariance. So you're just looking for a solution around that MUF value. So here, that's the thing. Yeah, we change MUF along the side when you change group.
So like, can I set the confidence like a value for each unit, or is that possible? Like,
yeah, for each unit and for each parameters of the like, so like for each unit you have its proportion, its covariance, its mean, and you have a confidence parameter for all three of them.
Right. So I think if you set the confidence level for a background high, and then others very small, I think that you may get the sense like a sort of what you want. I guess.
Yeah.
I'm not sure that's still capturing the covariance part, because like if you put the low confidence, like you know, also like both the median value and the covariance is kind of ignored. So I don't know like how you can just take the covariance part.
Where I'm going is that if you go into the DC example, right, and then the only thing, like, you want to figure out what your reference, what your background is.
Yeah.
That's always
it's always, yeah.
So I just want to know what the background is, and then the rest just solve for the unknown. So how would you do it?
Hey, sorry guys, I gotta run. So thanks, Thibault. I'll catch up with you guys next week.
Thanks, Lindsay.
See ya.
Lindsay.
Hi, Lindsay.
See ya.
Yeah.
Blockchain.
Thanks.
I would say two things. Like one way I would do it is that first thing you need to do is still to run a Tikhonov inversion. Just check your data that you can invert for it. So, like this framework is like how to go further if we have more information. I'm not trying to replace the Tikhonov inversion. It's really like, okay, if I have an area with a lot of information from the petrophysical side and from the geology side, that's one thing that's it's kind of my next step is that how I input this geological data here, like this classification, I can do a lot of things with that. Like it's also a lot of problem. And right now the way I'm doing it, it's like a maximum likelihood estimation, but I can also do a posterior estimation when I add prior information of that. If I have structural information or relationship information between the things. So it's like that's a thing that's like that I can do, but it's like still very in development right now. But yeah, like if you want the background value, etc., like try with some Tikhonov inversion. Maybe first see what's the background value, what's a good background value looks like for you.
So like that kind of like a little bit it's a little bit different what you said, right? Like because then you look at the background value and you're going to change your mean, right? Like not a confidence level for that. So you run the inversion. Now you got some, okay, those are the values, probably like what my inversion outputs. Then you're going to change that value of like your mean.
Yeah, but here he's saying that you have no information on that mean first. So
right. So like here, like in this case, it's assuming you're
it's different. I have some data. Can I change the data? Or I have no data. Can I choose the data?
Yeah. Let's suppose I got enough official data.
Yeah.
Without that, I run the L2 inversion. I got the output. The background value and my physical data is just like different. I got some scale factor, for instance. Right? And are you still going to decrease your confidence level, or are you going to change your mean value?
So your mean value of the inversions could be wrong just because it's not linear, and you pick something wrong in the beginning and you end up something wrong.
Yeah.
So you're going to decrease your.
You're still going to decrease your confidence level.
Yeah. Okay, but if you don't have no data, but you still need to input some means, then I mean both are possible. Like you choose a fairly low confidence, and you choose kind of your mean background. Like if you have no data, choose something. Yeah.
Right. Yeah. If you don't have any data, then it's more iterative process. You have to characterize a couple of values or structures and put that into
Yeah.
Put that in. And
But you can still put, but for the background, for example, if you expect it to be fairly uniform, put a very low covariance, like a very sharp one, saying, "Oh, that's my background." I don't know very much the mean. I don't have much confidence in that value, but please make it fairly tight around this value.
I think that would be a pretty similar result to the sparse version.
Yeah.
Like if you put a pretty hot, like a tight, even I think that if you actually like look at that, some that might be very similar. Yes, because you're putting the like a very tight variance, and then put the like a good reference model for the background, and then set the low confidence. I think it's probably similar to what the
The issue of L0 is the reference. Is that if you want to do reference, it's
yeah,
it
kills
everything
everything.
far, or you're going to go straight to the reference. And that's kind of, I think, where there's kind of a good corporation. They could be good corporation. You look at
But here, I think it's kind of similar problem, right? Like if your mean is wrong, then you're going to have a hard time with that. That's really wrong. I think it's probably very similar to the L2.
But then, if your mean is really wrong, then it's better that you put a zero confidence in that value, but put your confidence in the covariance, saying that I want to recover clusters. I don't know about the mean of this cluster, but please recover me some different clusters. And it might not work on all problems, but like it can definitely help you to get a bit further.
Yeah, I found usually with DC, it's usually okay. Like if that's relatively homogeneous, like that. So like looking at the family resistivity, picking up the highest histogram, and setting that as like that initial model, I think that's usually okay. And then you can adjust a little bit. Yeah, I like that. What I like about L0 inversion because you can play with that. So you can change the initial value and how sparse you can make it. So actually, that gives a good kind of like confidence on this is probably the right value.
So you run several inversions in this case, right? You can do the same here. Like if you don't not sure, like pick certain covariance or mean value, pick certain confidence, run and adjust according to the result. I don't have a claim that you run this algorithm once and you have the best answer. You like it's like any inversion thing. Like you're gonna run it multiple times if you want to have like the best possible result.
That was the reason why I asked like that, like how do you adjust that? But I don't know. I feel like I probably need to adjust the mean value. I guess because if you like a decreased confidence level, then I'm not sure where that's going to end. Because
I mean it's like from the math point of view, it's kind of the same because like it's a weighted average. So you have the confidence times the value. So if you decrease one or the other, like in the math, it's kind of the same.
Yeah, the algorithm is very good because the update process depends not on the value. When you're updating the means, it depends on how confident you are.
Yeah, but it's a weighted average. So it's like you have the observed mean times like plus your confidence times your prior mean divided by 1 plus your confidence. So like if you have this product of like confidence times of the mean value. So if you decrease one or the other, it's almost kind of the same.
yeah, that's good. Yeah.
So that's why it's like at the end of the day, it's maybe it's like almost the same, but like if you have actually information from the petrophysical data side, I would be more, and just from a philosophical point of view, I would be more inclined to decrease the confidence. But if it's a value, it means that you pick because you didn't have any prior information on that, then I would maybe change that value then just because it's a value you pick. So it's just like the difference between a user input and a data point. Like you're not gonna change your geophysical data value if you didn't fit it well. You're gonna either remove it or add noise, which is correspond to add uncertainties or decrease the confidence.
Well, like we're getting a lot of knobs now.
Yeah, I mean, it's a still like there is a lot of things to do with that framework that I have not tried or like I've as I say, like right now I think if you look at the framework like this, as a group here we figure it out well, like that's SimPEG, that's the UBC code, etc. This part is really a thing that I spend most of my time, like how to include this information and having like weighting and reweighting schedule for the betas, the alphas, and the weighting of the data is fit together, like having some directive that takes a lot of care for you that just to make it work. Like it's not in the math, but like, okay, I need to get some idea of which parameter to choose. So most of it is based on like what we do it for the beta, like compare the eigenvalues of each thing and put it to a certain level compared to each other, or like your confidence. So like kind of like more engineering thing. And then my next step for me would be like, okay, how do I do this update to like not only pick it based on the value of the model cell, of the geophysical model cell at this point, but also to include other type of information prior or like relationships to grow. So that would be the next step. But like there is a lot, yeah, there is a lot of parameters that's added, but it's not more it's more parameters that comes because you add other information. I don't add parameters on the geophysical side. It's like you have on the geophysical side, you already choose a lot of parameters because of the geophysical data. Your synthetics right, we do the same, but we add more data, we have more parameters. I cannot go against that.
Cool.
Oh, that was just a very like some playing here. It's like I was having like it's a weird model, but it was basically like if I was doing a Tikhonov inversion, like that was a Gaussian, but I can also compose this Gaussian with like I can have each of my Gaussian to have its own mapping in SimPEG. So then I can have like cubic or quadratic relationship also to include into that. So it doesn't have to be just to say that we assume Gaussian, but in some space, so we can also include nonlinear relationship between the two. It's not. It's not. That's not a limitation.
I'm looking for it. Actually, if it can have a petrological data that looks like that.
Yeah,
I have no idea.
Doug was curious about that, so I delivered. But I'm not sure.
I think we should really ask Randy.
Oh yeah, no, Randy would be.
And I think that Randy may have some.
Yeah, so it's already 11. That's why. Like yeah, if I can just like maybe like in a very quick way. I hope I'm on the right branch, but yes. So so I have like a class petrol regularization, and I have like now it's like a petrol smallness class. And I did a bit like what you did with Tikhonov and simple, so like petrol smallness and petrol regularization takes the volume, whilst I have a simple petrol smallness that doesn't take the volume. I prefer the one with no volume, but I just try to tie also the development to what was already inside SimPEG, so people like you have yeah, so I'm almost never using the one with volume at all.
Simple. I think we probably need to wrap it up.
Yes.
I just got a question. Like, is it structured like a? So let's say you're ground and mag. Is it like a different regularization, or like a different regularization class, and you're kind of summing that up using the combo objective function, or like you're like your big petrol regularization that handles those two.
Half and half. Like so So first way I implemented that was having the petrol regularization to take it all.
Mm-hmm.
So I was using so in my objective function I have the smallness, which takes the whole model, all the physical properties, and then I was adding the separate smoothness for each physical properties. The problem with that implementation is that it's in each combo objective function you have one alpha x, one alpha y. So I was applying the same alpha for each smoothness, which is a big of an issue because, for example, grav and mag, the scale of each physical property is completely different, like order of magnitude different. So you have alpha times the gradient of one physical property and the same alpha times the gradient of the other physical property. So one of the smoothness is actually not is actually overcome compared to the others. So that was my first implementation, to have to have it all at once. And it's fine, but it's at the implementation, after that it's kind of weird, you cannot put a different alpha x, for example, for the two different physical properties. So the other way I'm doing it right now, maybe I will need to. Sorry, I think I'm gonna have to pull because I've not been using my Mac recently with. Oh, so now I just have a utils dot make petrol regularization, and and that's how it puts your reg object, and what it does out of the hood. It's a combo objective, but it's the first term is the smallness that takes the whole model with all the physical properties, and then I have a reg smooth property one. So the smooth, so I have the smoothness for the property one and plus another smoothness for the property two. So I'm actually adding it's a real combo, reg one plus reg two plus reg three, and so each one has its own alpha x, etc. And I have a utils that does that now.
Okay. For usability, it would be better if it was just for a combo. Can you implement that?
No, I've tried. We actually had a talk last week with Lindsay because I was I don't want to always add that into things. And but the thing is, when you develop in the regularization class, that would require to do, for example, in your objective function to add regularization dot, for example, regularization dot simple plus regularization dot, to add several regularization dot simple. But the way you add things in the objective function in the class, in the regularization class, it's looking for a multiplier pair each time. But the multiplier pair has the alphas, but if you add several regularization class, they don't have multiplier pairs. Regularization.simple doesn't have a multiplier pair. So you cannot make that addition under the hood in the regularization class. It has to be in the util outside.
So you just need because you don't have a multiplier.
Yeah, because when you do the plus, then the multipliers are taken from that addition, but there is not a beta 1, beta 2, beta 3. There is not a multiplier pair there. So there are some assumptions in the regularization class that prevent you to actually create a combo objective as a class.
I think it will be beneficial. So I think it's a different level. You've got a separate regularization. There's one other regularization that actually hits everything.
Yeah.
So I think that's the framework that we want to have, because it's very abstract framework, because people's physical constraint actually fits in. But anything during types of regularization, cross gradient or whatever, actually if you can have that frame, it's nice to have that, because that can. That can make a linkage between different objects. But I think it's probably not very good. But,
yeah, and even now, with my implementation there, I had to rewrite something because I was breaking some assumption of the combo objective. For example, my smallness now it takes all the physical property, but each smoothness takes one physical property at a time. So each term of they don't have the same mapping, but it was assumed that regularization, everything has the same mapping all the time. It's not the case for me anymore. So that's one thing. Yeah, it's like a lot of like the property things and validator, like saying that everything should have the same mapping, but it's not true, for example, for me. Just because like the smallness takes all the physical properties, the smoothness takes them one by one. That's one of the things.
Yes, a lot of details.
Yeah.
Deepan's gone. Deepan's gone.
Okay.
So, hey, Deepan, we're finishing up. Any other comments or questions?
Putting more for us.
Yeah. Thank you very much, Tigo.
Thanks.
All of us.